all different types of measurements, and this is where we unlock something called the normal model. Pay attention, my friends. This is likely the most important lesson in the entire masterclass. Now, we know that a histogram follows a roughly bell-shaped curve, which is very peaky in the middle and has a couple of tails out either end. Now, we have a measurement, a standard measurement, a standardized measurement of its center, and we've also explored the standardized measurement of its variability. But what if we had a standardized measurement of the significance of this variability? This is the magic question. Thankfully, there is a method of standardization for variability, and this is called the Z-score. On the screen, what you'll see is the Z-score formula. This is very important to memorize. I would recommend you taking a note of this. And you will also see the standard normal model where we have the Z-scores laid out like so. Now, here in the formula, you can see that we have the data point and the mean and the standard deviation. Now, you have to understand that this is very important. One Z-score is equal to a standard deviation. This is because if you have a data point that's on the standard deviation and you're dividing it by the standard deviation and the mean, it's going to equal 1. This is where Z-scores come from. They go 1, 2, 3, 4, 5 out to one side, and -1, -2, -3, so on and so forth out to the other side. This way, when we form a Z-score of something, we form a standardized measurement of the significance of its variation, and this enables us to compare different data sets together. So let's dig deeper. Fun fact, the reason why a Z-score of 1 is so significant in the world of stats is because when you look at the normal model, you can see that the inflection point in the rate of change of the data, it's actually when the probability density of that data declines the fastest. That is where the standard deviation point is. That is the inflection point. And that is the reason why it's so significant. So, because Z-scoring maths and standard deviation math is so incredibly important, this is the only time in the whole masterclass where I'm going to mandate a little bit of math work so that we can actually understand the significance of this. But to make it a little more interesting, we're going to use pizza. That's right, we're going to use pizza as an example here. We're going to use the delivery times of some of your favorite pizzas to figure out exactly why this is important. So let's have a look at it. So imagine we have a whole bunch of information on the distribution of pizza delivery times in your local area. Now you can see that the average pizza delivery time is 30 minutes. But of course, there's always going to be some variability. So we can see that one standard deviation above the mean is 35 minutes. This is because the standard deviation is 5 minutes and the mean is 30. And if we go one standard deviation below the mean, we have 25 minutes as the average delivery time. So the average variability goes somewhere between 25 minutes to 35 minutes. Now, this is where the Z-scoring comes in. Remember the Z-scoring formula. It is data point minus the mean divided by standard deviation. You can see that if we take the measurement that is one standard deviation away from the mean, which is 35, and we subtract the mean from that, and then divide it by the standard deviation of 5, it gives us a Z-score of 1. This is one standard deviation. You can do the same experiment with 20 minutes. 20 minutes minus 30 minutes, which is the measurement, minus the mean, divided by standard deviation of 5, gives us a Z-score of -2. Likewise, you can go all the way out to the right-hand side. If your pizza delivery was to come at 43 minutes, and you take that away from the mean, and you divide that by the standard deviation, that is a Z-score of 2.6. Now, Z-scores are all well and good. However, we want to ask the question, what does this mean for probability? Because I've been teasing this entire way through the statistics, which is, how do we use standard deviations, how do we use variability to model probabilities? And this is where the magic of it comes in. Well, the secret is actually contained within the normal model. You'll actually find that the secret in the normal model is actually in its shape. You'll find that the shape of that distribution in statistics actually enables you to anticipate the probability of an event occurring. And this is what we're going to explore here. What you'll see on screen now is 2 examples of normal probability distributions with their probabilities marked on them. You see the top example here. 68% of the variability is contained within one standard deviation of the mean. 95% of the information is contained within 2 standard deviations of the mean. And 99.7% of the information is contained within 3 standard deviations of the mean. And of course, in the other distribution, you can see this broken down in a more granular fashion, which is important for some applications. However, the top one is the most important. You can see The implication of this is that the majority of the information is kept around the mean. This makes sense because of the measurements that we've taken with our variability. What does this mean in practice for your pizza delivery times? This means that there is a 68% chance that your pizza gets delivered within 25 to 35 minutes. But what if we wanted to go one level deeper? What if we wanted to really explore this in a different way? Let's ask a question. What is the probability of your pizza being delivered in less than 17 minutes? Of course, what you would do is you would put this into your Z-score formula, and then you would reverse engineer this with a probability table. So you would put 17 minutes minus 30 minutes for your average, and then divide it by the standard deviation of 5. This gives you a Z-score of negative 2.6. If we wanted to find the probability of this event occurring, all we have to do is take the Z-score that we've calculated and plug that into a normal distribution probability table. We know that the Z-score is negative 2.6, so we put that into the table. With negative 2.6, we find that the probability is 0.47%. So the probability of your pizza getting delivered in less than 17 minutes is 0.47%. What if we wanted to do another example, just to really cement this, and ask the question, what's the probability of us waiting more than 47 minutes for our pizza? Again, Z-score formula. 47 minus the mean divided by the standard deviation. Our Z-score is 3.4. Probability distribution density of 3.4 with our Z-score gives us a cumulative probability of 0.03%. There is 0.03% probability that you'll wait longer than 47 minutes for your pizza if everything goes to plan. So what can go wrong? There is a risk that when you learn about Z-scoring and about the normal model, that every problem that you come across is going to look like another application of the normal model. While the normal model applies to most data sets in practice, it doesn't apply to all of them. So you actually need to go into the data and make sure that the histogram is unimodal. Make sure it's symmetric. Make sure that there's no errors in the data. It's only when it meets these conditions that you can actually use the normal model successfully. Or if you have a stationary time series that is evenly distributed. Some stationary time series have massive skews to one side. You have to be always looking for these different types of things to make sure that the model that you're using is appropriate. Now, a very basic example of this type of research in the wild, taking something and then Z-scoring it, is actually the Z-score indicator on TradingView. If you pull this one up, you'll see in this screenshot example that I have here, that what we have is a measurement, a Z-score of the price moving away and towards an average. This actually reveals the significance of how far away the price has moved from the average measured in Z-scores. If you believe that the behavior of price is approximately normally distributed, then you can see how this is a natural extension of the same principle, and it gives us a bit of a decent idea of the overextension of price in one direction or another. This is an extremely basic example. I wouldn't go out and use this particular example as a practical indicator. It's very simple, it has a lot of pitfalls. However, it's just a great example of seeing this in the wild. So this bell curve shaped piece of information that we have called the normal model, it has a standardized measure of center, which is the mean. It has a standardized measure of variation, which is the standard deviation. And then we have a standardized measure of the significance of the variation called the Z-score. Combining all of these pieces of information together, their measurements, and knowing when to use them is the crux of good statistical analysis. The practice of Z-scoring allows us to calculate the probabilities of a certain event occurring at any point within the distribution. As you can probably tell, this is very significant for us. This is very important because when we have other pieces of information that tell us things like valuation for Bitcoin or sentiments data or indicators like this, we can know approximately the importance of that state occurring within the context of the normal model. You can tell from the pizza example alone that having a good understanding of how to model these Z-scores, how to understand the probabilities behind them, is a fantastic way of setting your expectations for the outcomes of certain events that have been historically occurring. Obviously, this translates directly into findings when we take information from different indicators in the analysis section of the masterclass, when we're looking at them and understanding how to measure them. So this is all very important stuff. Hopefully you enjoyed this lecture, and I'll talk to you in the next one.